Good evening, class. Greetings from Orlando, Florida. I'm spending some time this evening to pre-record this lecture for you in preparation for exam number 2 that's coming up. This lecture represents the last lecture that is going to be on exam number 2, or at least that is what I call fair game on the exam. And really, there's nothing new that we're going to really teach you in this lecture. It's just going to be, I guess, some new practice of things that you've already been taught with regards to settlement. Really what we're going to be dealing with today is settlement beneath foundations. And what I mean by this, let me pull up a little whiteboard here to show you. So if I have the ground surface and I have some soil layer down here of interest where I have the center point of that sublayer, and I'm interested in computing what the settlement in that soil layer is going to be. Everything that we've learned thus far in this class, or at least when we've talked about settlement, is saying let's assume that there's going to be some infinitely long load of some stress applied to the soil. Well, we're going to change that, and instead we're going to apply some finite load. And you guys all have experience with finite loads because you remember these are like where we use the isobars. They're the isobar solutions or the Boussinet elastic solutions to try to estimate the influence zones beneath the soil. And so the point is that at whatever point this is, it's going to have a different stress than, say, right there, than, say, maybe this point in the soil, just at a different location that maybe isn't beneath the footprint of our load anymore. And it may be different than this point over here. Why this is significant is because, let me choose a different color here, maybe blue. If I were to plot then the settlement profile, or what I think the ground surface would look like after this thing is settled, it might look something like that, where we get a little bit of settlement outside the footprint, most of the settlement beneath the middle of our load. And then again, as we get away from the footprint, we'd expect to see less and less and less settlement. So really, this is all that we're going to learn and apply today, is how do we compute settlement beneath finite loads such as foundations. And the real trick is that you just got to compute the settlement at different points horizontally beneath your applied load. Because at all these different points, the change in vertical stress is going to be different, because the influence factor from our footing is different. And you'll remember that delta sigma z is equal to q times the influence factor. That's all we're talking about today. So basically what this introduction slide is just telling you everything that I just said. We're going to focus on footings. We're going to focus on stress beneath footings. And the only difference between what you guys have already done on your homework up to this point and what we're going to learn in this lecture is that the induced stress, or that delta sigma value, is going to change depending on where you are beneath your load. It's not going to be uniform everywhere because we're not applying a uniform load anymore. So the best way to demonstrate this is we're just going to walk through a simple example. And I'm going to go through the entire part, or the entire work of this problem, and walk you through it. And I strongly recommend that you go through this type of problem as well. You're going to on your homework anyway. But I think it's a good idea to try to recreate the values that I compute in this problem so that you can be comfortable with the fact that you can compute settlements beneath footings. So let's say that here's the problem that we have. We have a multi-layer soil system that's comprised of a loose to medium dense sand that's 10 feet thick. Here are the properties of the sand. Beneath that we have a 15-foot saturated clay layer that we've obtained these properties for. We have the compression index of 0.18, a recompression index of 0.12, a coefficient of consolidation equal to 30 feet squared per year, saturated unit weight of 120 PCF, an initial void ratio of 0.85, and then we have a modified secondary compression index of 0.008, and we're going to say that the over-consolidation ratio, which you'll remember is the pre-consolidation stress, that's a P, divided by the current effective stress in the soil. And that's equal to 1. So what that means is that the soil is normally consolidated. And then below that, we're going to say that we have a gravel soil that extends as deep as we can drill. And the SPT resistance for that soil on average is 50 hammer blows per foot in the soil. What we're going to do as engineers is we're going to build a circular tank, a circular load on the soil that's 40 feet in diameter, and it's going to have a uniform applied pressure of 1,500 pounds per square foot. So here are the things that we need to find. First of all, we need to find the total immediate and primary settlement beneath the center of the circular tank. The second thing we need to find is how long is it going to take for 95% of primary consolidation to occur. We're going to assume that 95% is 100%. Why are we going to assume that? Well, because if you'll recall from Tertsagi's consolidation theory that you can never have 100% consolidation. That takes infinity to achieve. So we're just going to assume 95% is close enough to 100%. And that's what's done in practice a lot of times, by the way. And then we want to compute the amount of secondary consolidation settlement that will occur beneath the center of the tank 3 years after primary consolidation settlement has finished. So those are our goals. Here we go. First, let's look at the immediate settlement. Now remember, there's two ways we could tackle this problem. We could use the theoretical elastic solution for settlement, or we can use the Meyerhof empirical equation for settlement. I like Meyerhof just because it's easy. There's the bane of my existence again. That should be an A for coarse grain soil. Forgive me, please. We're going to go ahead and use the Meyerhof empirical equation to solve this. Again, you could use whatever one you want, but you have to use the right equation based on the information that's given. And remember, what we are given is SPT blow counts, and so that's why I like this equation, is because we can go straight to a solution. So you got to remember then that immediate settlement, we're looking at coarse grain soils. So what does that mean about the clay layer in the middle or sandwich between our sand and our gravel? What does that mean? Well, it means we're going to ignore it. We're going to ignore the clay layer and only consider the sand and the gravel layers in this immediate settlement. So, I mean, one thing that I could do, I could go back, of course, and look at this layer, and I could use the Boussinet elastic solutions for a circular load, and I could get my zone of significant stress and weight the thickness of that sand layer by the thickness and the thickness of that gravel layer, and computing that average SPT blow count. I could do that, and that certainly would be appropriate. But here's the deal. That would take a little bit of extra work. If I look at the blow count from the gravel, that's a lot higher than the blow count in the sand, which means that I'm not going to get a whole lot of predicted settlement from this gravel. So what instead, if I just assumed that value of n equals 12 for my average SPT resistance? Not only would that be conservative and would likely be overestimating the prediction slightly, but it would also be a lot easier. And so that's what I'm going to do. What I'm going to do is just assume then that the sand, the blow count from the sand, is what I'm going to use in design. And remember, this is a design decision. There's no like right way to do this per se, but this is just something I've learned through my own experience. And so if we're doing a homework assignment, if you wanted to compute the average SPT resistance using a harmonic mean like you've practiced on your earlier homework assignments, you're more than welcome to do that. But this is just a nice conservative approach that's a little easier to do. And I'm certainly interested in training each of you to be engineers that can make these types of decisions where you simplify things, maybe come up with some conservative results. Those are very handy skills to have. So here we go. Here's the equation we're going to use. We just have to plug everything in and make sure that we're using the right units. So Q, you'll recall, is equal to 1500 PSF, but remember that Q has to be in units of KSF. So it's 1.5 KSF. And our average blow count we're going to assume is 12, and that's from the sand layer. We have to compute F sub D. F sub D, remember, is a factor to account for the possibility that our footing is below the ground surface or at a buried at a little depth. This is right on the ground surface. So when you're right on the ground surface, F sub D is equal to 1. Okay. And then B, or the width of our footing, so this is a circular footing, we're just going to apply the diameter to B. I know it's not a square, but we'll treat it as an equivalent square and just put in that 40 feet. All I have to do now is crunch out this number, and it's going to give me my settlement in inches. And I get ½ an inch. So this is the estimated immediate settlement directly beneath the center of this circular footing. Here's a question. How long will it take for this settlement to occur? Well, that's why we call it immediate settlement. It will occur immediately as soon as the load is applied to the soil. Okay, so remember, total settlement is the summation of elastic settlement plus primary consolidation settlement plus secondary settlement. So we already have elastic settlement out of the way. So all we need to do is get these two now. So let's move on to consolidation settlement. Consolidation settlement, we're going to focus only on the saturated clay layer. In reality, we'd also focus on any clay layers that were not saturated. I'd probably treat them as if they were saturated to account for the possibility that groundwater could rise at some point during the lifetime or the lifespan of that structure that we're building. Again, that's a conservative assumption, but it simplifies the calculations immensely. So we're only going to look at the clay layer. The clay layer was 15 feet thick. Let's divide the clay layer into 3 sublayers that are 5 feet thick each. Again, this is my decision. If you wanted to divide it into 5 layers that were 3 feet thick each, you could do that too. It's just up to you. There's nothing magical about the 5-foot number that I picked. Now, in order to compute the primary consolidation, we need to compute the induced stresses. That's our delta sigma. And remember, delta sigma is going to come from our induced stress beneath the circular load. So we're going to apply the Boussinet solutions to estimate what the induced stress is beneath that circular load. And since we're right below the center of the load, we can use this equation that I gave you when we were talking about elastic induced stresses beneath different shaped loads. So this is for a circular load, and it's beneath the center. So you see that this equation is a function of depth. It really matters how far below the center of our circular load we are. It's a function of the radius of our circular load, and it's a function of the uniform stress that's represented by our circular load. So if you recall, let's change that color. Let's go back to black. That's the ground surface. I had 10 feet of sand, and then I had 15 feet of clay. So what we're doing is we're subdividing this clay into 3 layers. So I'm going to compute, well, let's see, here's the center, here's my circular load, and I'm right beneath the center of it. So I want the depth to the center of each of those 3 layers. That's really what I'm after. So you can see that the depth to the center of the first sublayer is going to be 10 feet of sand plus 2 feet of clay, so that's going to be 12.5 feet. For this next layer here, that's going to be at 17.5 feet, and that's going to be at a depth of 22.5 feet. So let's compute the depth to, let's compute the induced stress at a depth at the midpoint of the first sublayer, which is again the 12.5 feet below the ground surface. Now remember, the load radius, because the diameter is 40 feet, the load radius is just going to be 40 feet divided by 2. So here we go. We're going to use this equation right here. Plug in Q, 1500 PSF. Radius is 20 feet, and my depth below my ground surface is 12.5 feet. So I get 1,277 pounds per square feet. That's my delta sigma. That's the increase in the stress from my applied circular load. If I were to make the same calculation for my other 2 sublayers, I get an increase in stress of 1,072 pounds per square foot for the second sublayer and 874 pounds per square foot for the third sublayer. Okay, so let's hang on to those. So now let's go to our settlement table. I've taken the time to fill in most of this table, but I left a couple of blanks just to show you the different things that I'm computing. Now remember, thickness, initial void ratio, the compression index, the recompression index, those were all given to us, and that's why they're all filled in here. Remember, this is the total stress. We know how to compute that. This is the hydrostatic pore pressure, and that's just the depth below the water table times the unit weight of water, and this is just the effective stress, where remember, effective stress equals total stress minus pore pressure. This is my induced stress for my circular load that we just computed on the previous page, and this is my pre-consolidation stress. And I get that from my over-consolidation ratio. Because my over-consolidation ratio is equal to 1, I know that my pre-consolidation stress is going to equal my effective stress. So that's why these values are all equal. If my over-consolidation ratio was a higher number, it would change what my pre-consolidation stress was. Okay, so let's start. You can see I already took the liberty of filling in the missing depth for my second sublayer. This is depth below the ground surface. When I'm computing total stress for the first layer, let's go ahead. That's just going to be the moist unit weight of the sand times the thickness of the sand plus the saturated unit weight of the clay times the thickness of the clay down to the center of the first sublayer. So I'm just filling in values now. So I have 105 pounds per cubic foot times 10 feet plus the saturated unit weight of the clay, which was given to us, times the depth into the clay layer minus, or I'm sorry, the depth from the ground surface, that's this guy, depth from the ground surface minus the thickness of the overlying sand. So if I compute that for my first sublayer, this is 105 times 10. That's this guy right there. Here's the 120. That's the saturated unit weight. And then there's the Z minus 10 feet. That's this relationship between depth below ground surface and the thickness of the overlying sand. So if I compute that, I get 1,350 pounds per square foot total stress in my first layer. Okay, I left a blank down here for the third sublayer for pore pressure. Now you'll remember that the water table was right at the top of the clay layer, which means that if I'm right down here at the middle of my third sublayer, then the depth down to that from top of the water is 5 feet plus 5 feet plus 2.5 feet. So that's going to be 12.5 feet into my, or beneath the bottom of my water table. So I just developed this relationship here, which is the unit weight of water times, again, the Z minus 10 is just the depth below the top of the clay layer, or in this case, because the water table is right at the top of the clay layer, it's also the depth below the water table. I would have to adjust that equation if the water table was located at a different depth. So anyway, when I compute and I plug in this 22.5 into Z right there for that equation, I compute a value of 780 pounds per square foot for my water pressure. And then I compute effective stresses as total stress minus pore pressure, and that's where I get all of these values from. Okay, now induced stress, you are going to remember that we computed that already for the circular loads. If you can't remember how to do that, go back to the previous slide and you'll see where we got those. For our first sublayer in the clay, we computed 1,277 pounds per square foot. And then here are the other induced stresses for the other two sublayers. And I already explained the pre-consolidation stress. So then, in this column, we're just going to add the effective stress to the pre-consolidation stress. So that's just this column plus this column. And that's how I get these numbers here. Okay. Now we need to decide what case it is. Now this is tricky, remember? We know that the soil is normally consolidated, meaning that the current effective stress is equal to the pre-consolidation stress. And whenever the soil is normally consolidated, we know then that the soil is going to be a case 1. What I call the case 1 from the consolidation lecture. So if it's case 1 and the soil is going to stay consolidated, we're going to use this equation to compute settlement for that sublayer. If it was case 2 where the soil stays over consolidated, meaning that the pre-consolidation stress is greater than the initial effective stress plus the change or plus the induced stress, then it would be case 2. If the soil was a case 3, meaning the soil started over consolidated, but became normally consolidated after we applied the induced stress, then that's going to be a case 3. And as you can see, in this particular instance, we are all case 1 because we started normally consolidated. In order to have case 3, the soil has to initially be over-consolidated, meaning the over-consolidation ratio would be greater than 1. Okay? So, because we have case 3 soils, we're going to use this equation right here to solve for our settlements. And go ahead and all we're going to do is plug and chug on all of these values, folks. And so pull out your calculator, punch in these values, and see if you can get the same settlements in feet that I computed here in this table. Once I have all my sublayer settlements, all I need to do is add them up and get a total settlement of 0.354 feet, which is the equivalent of 4.25 inches. So that is my primary consolidation settlement. So going back again, if total settlement is elastic settlement plus primary consolidation settlement plus secondary settlement, I've got those two, and now all I need to do is get the secondary settlement out of the way. But before I do that, you'll recall that the problem asked us to compute how long it's going to take primary consolidation to do that, or to occur. So to compute how long for the whole clay layer to experience consolidation, I'm going to use U average, or the average degree of consolidation for the entire clay layer. So you'll recall from our previous lecture that the average degree of consolidation is a function of our time factor, T sub V. That's from Terzaghi's consolidation equation. And you'll recall that T sub V is a function that's equal to the coefficient of consolidation times the time divided by the maximum distance for a drop of water to drain out of the soil squared. So if we reorganize this equation to solve for time, then the equation is going to look like this. Okay, so this clay layer, because it's sandwiched between a sand layer and it's sandwiched between a gravel layer, we know that the soil itself is going to be double drained. And because it's double drained, that means that HDR is going to equal the total thickness of the clay layer divided by 2. So the clay layer is 15 feet thick. We're going to divide it by 2, so that means that HDR is equal to 7.5 feet. And C sub V, the coefficient of consolidation, remember this was given to us, that's 30 feet squared per year. So time for consolidation is going to equal 1.875 times the time factor. So here are our equations from Terzaghi's 1D consol equation. And all we're going to do is use these two equations to fill in this table, where this is, remember, U average, this is the average degree of consolidation for the soil. This is simply equal to primary consolidation times the average degree of consolidation. And this is our time factor right there, and then this is the time for that settlement to occur. So if I have 10% degree of consolidation, well, 10% times my computed consolidation settlement is just going to be 0.43 inches. Because remember, I computed 4.3 inches of total primary consolidation. So this is just saying 10% of that. And then if I compute 20%, that would give me 0.85. 50% would be 2.12. 90%, 3.83. And so you see what I'm doing there. And then all I have to do is compute the corresponding T sub V value from that degree of consolidation, and I'm going to get that from these equations right here. So these T sub V values are computed from these two equations. So at 50%, that's going to be a T sub V value of 0.197, which we talked about in an earlier lecture, and for 90% it would be 0.848. So now I'm going to plug those T sub V values into this equation right here, which will give me the time for consolidation for that my specific clay layer. When I plug those T sub V values in right here, these are the number of years that's going to take for the soil to experience that much consolidation. Now, 95% consolidation was my target. That's a T sub V value of 1.129 according to this equation down here, or the second equation from Tertaggi. So when I plug that 1.129 in, I get 2.12 years for 95% consolidation to occur in my clay layer. Now, if I take these values right here for time, and I take these values right here for settlement, and I plot them, actually I'm going to plot them you can either plot them upside down or however you want it, but this is going to be time and this is going to be settlement. What I expect to see is that with time, I'm going to get something that looks like this, right? That's something I want to plot. And so that's what I'm doing right here, is I have my time versus years, and I have my settlement plotted right here. Now I have them in negative numbers, meaning the soil is deforming down. I mean, you could do it however you want if you want to make them positive numbers. I always liked using negative numbers because it just helped me keep the direction of the movement. It always let me keep it straight, basically. So notice, by the way, at time equals 0, that I have an immediate settlement of 0.5 inches. Where is that coming from? Well, remember, that's coming from the immediate settlement that we computed from our sand layer. So we have an immediate settlement of 0.5 inches, and that's why all of these individual settlements are the primary consolidation settlements plus the immediate settlement of 0.5 inches. Okay? So cool. So now we can predict what our settlement should be with time after we apply our load on the ground. One thing to point out here, a question we could ask is, why don't we use the average degree of consolidation for 100%? Again, because T sub V would be equal to infinity, and no contractor has that much time to work with to build something. Okay, last and final step, we're going to predict secondary settlement. So again, total settlement is what we're after beneath our footing. We've already computed the elastic settlement or immediate settlement. We've computed the consolidation settlement. Now we need to get secondary settlement beneath the center of our footing. And remember that secondary settlement is a function of time. It's not a function of stress. Okay? It is not equal to a function of stress. So here's the equation that I gave you to compute secondary consolidation settlements. This is our modified secondary compression index we get from a time rate curve. This is the thickness of the entire clay layer. This is the time for primary consolidation to end. And remember, we computed that in this previous calculation, the time rate calculation, as being 2.12 years. Now that gave us again 95%, but we're just going to treat that as 100%. So for this problem, that's 2.12 years. And then remember, T sub 2, this is going to be the time to primary plus the time of interest, which in our problem case was 3 years after we assumed primary consolidation has ended. So here we go. Here's our modified secondary compression index. It was given to us. Here's the thickness of the clay layer. That's 15 feet. So now we just need to plug in T2, and that's going to be T sub P plus the time of interest, which is 3 years, all divided by T sub P, which was again the 2.12 years. So I make that calculation and I get 0.55 inches for my secondary compression index. Now, if this secondary consolidation settlement is too large and the owners or the structural engineers are squirming because it's too big, then what could we have done to make this modified secondary compression index smaller? Well, we could over-consolidate the soil by surcharging it. If we over-consolidate the soil and make the over-consolidation ratio much greater than 1, then this C sub alpha prime gets smaller and smaller. So if we surcharge it, add some wick drains, that's going to lower that predicted secondary settlement substantially. Alternatively, we could apply some ground improvement techniques to just stiffen the ground itself. That's a different topic for a different day, but it is an option of something that we could do. So here we go. Total settlement. It's the summation, we'll come back, it's the summation of our elastic settlement, our primary consolidation settlement, and our secondary consolidation settlement. So 3 years after primary consolidation ends, which would be 2.12 years plus 3 years, we are simply predicting that beneath the center of this circular load that we're applying to our soil, we will have had a total of 5.3 inches of settlement. So I know this was a very detailed example, and I apologize if it seemed a little slow in places or times, but I really wanted to work through this step by step so you could see how everything comes together. So again, I encourage you all to take some time to go back through this, rework this problem yourself, and then have additional practice on the assigned homework problems, and then you'll be more than ready for exam number 2. So with that, thank you everybody. Appreciate your attention, and I hope you have a wonderful day.